Hello students, welcome to Educate. In the last class, we have discussed about chemical properties of alcohol, phenols, and in this class, we will firstly discuss about some commercially important alcohols and the ether. But I have left the mechanism. In our 12th board examination, question will ask from the mechanism, and there is 3 questions related to mechanism. That means of the 3 reactions, you will have to discuss about the mechanism of reaction. So we will discuss later on also. Now in this class, we will discuss about the commercially important alcohol and the chapter ether. Let's see. Commercially important ether alcohol there. First one is here methanol. Methanol. It is also called wood spirit. Also called wood spirit, methanol. Why it's called wood spirit? Because it forms by the fractional distillation of wood. That's why it's also called wood spirit. Now, what's the reactions here? That's the reaction here. Very simple. Keep in your mind that. That is, in the catalyst of zinc oxide and chromium trioxide, the hydrogen will be acted on carbon monoxide and there will be formation of methanol. This methanol is poisonous and at the smaller concentration also it have the hazardous effect. Like that, it at low concentration it will cause blindness, and if the concentration of methanol will be more, then that causes death. So that is methanol. Okay. Then after is ethanol. Ethanol here, that's a very important compound of alcohol, and how it forms. You know that is alcohol, that is sarab, wines, you have heard about that. So what is there? That ethanol commercially forms when the sugar will be treated with here. Firstly, when the sugar will be treated with Jammage enzyme. Firstly the sugar here, invertage enzyme acts on the sugar. Firstly, invertage enzyme acts over the sugar, and there will be formation of glucose and fructose. I have already told you both glucose and fructose are enantiomers. Means both will have same molecular formula but opposite optical activity. Glucose is dextrorotatory and fructose is levorotatory. So when the enzyme invertase acted on the sugar converted into glucose and fructose. Invertase enzyme, so because there is inversion of sugar, sucrose is dextrorotatory compound, and after hydrolysis it becomes glucose and fructose. After hydrolysis, sucrose converted into glucose and fructose, of which glucose is dextrorotatory and fructose is levorotatory. And fructose rotate the plane polarized light towards left through greater extent. So initially this one is sucrose is dextrorotatory and fructose here resultant solution is levorotatory. So that's why there is inversion of sugar. This phenomena is called inversion of sugar. When hydrolysis of sugar will be done, then glucose and fructose will form, which will be levorotatory. So this phenomena is called inversion of sugar. So name of the catalyst is invertase. Okay. Then after here on glucose here, the enzyme jammage. Then the enzyme jammage acted over that, and there will be formation of alcohol and CO2. This one, nothing here. From here, questions don't ask so much frequently. Yes, one thing keep in the mind. What is that? The wines, that is ethanol, also manufactured by grapes. Might be a number of persons have heard about the that this wine is made up of grapes. What actually is here? In the grapes, the firstly the when that's ripen, when the grapes ripen, then the invertase enzyme acted over the sucrose, and that's converted into glucose and fructose. At the surface of the grapes, the enzyme zyme is formed there. What is there in the grapes? Might be you have seen the white spots there. That is nothing. That is yeast, and in the yeast there is an enzyme gymase. When the grapes will be crushed, then the yeast will comes in contact with the glucose, and then after glucose as well as fructose, and then after this glucose as well as fructose will convert into ethanol. Yeast is respires anaerobically. That means yeast oxidizes anaerobically, means respiration in yeast takes place in absence of oxygen. There is two types of microbes, aerobic and anaerobic. We are, the human beings, animals, plants, we are aerobic. Aerobic means our metabolic activity takes place in presence of oxygen. But in case of yeast, the metabolic activity takes place by the anaerobic respiration. That is the part of the biology you will study. If you are not the student of PCM or PCB, then no need to discuss about that. And if you are the student of PCB, you study there in the biology detail. So here the yeast will comes in contact with glucose and fructose, and there will be formation of ethanol, and CO2 gas will release from there. When the ethanol comes in contact with oxygen, then oxidation of ethanol will take place, and there will be formation of this ethanol will convert into ethanoic acid. Okay, and one interesting fact here: when the concerned 14% ethanol will form, then after there will be the activity of the gymase enzyme will inhibit. When there will be 14% alcohol, then there will be no formation of alcohol. That means the formation of alcohol will stop there naturally. So when the wines are made by the grapes, then there the concentration of ethanol will not exceed 14%. Okay, that's why this might be, I don't know, because I have never taken the drink alcohol, so I am not aware about their cost, but I have heard that the cost of the wines which are manufactured by the grapes are highly costly. So that is here. Then after most frequently asked question in 12th board examination is about denaturation of alcohol. Very important point. 2 marks question in the 12th board examination. Question asked about the denaturation of alcohol. Simply question will be write about denaturation of alcohol. So listen, what happened? The manufacture of alcohol, that is not so much costly, but government will have to take tax or to the any reason. So that make unfit for drinking. To make the alcohol unfit for drinking, the compounds of copper are added to impart color in the alcohol, and the compound and the pyridine is added to impart foul smell. To make alcohol unfit for drinking, the compounds of copper are added to impart color, particularly blue color, and pyridine is added to impart foul smell. That is called denaturation of alcohol. Okay, so in the 2 marks question, what you will write? I'm writing here because this point is very important. So, and it is not difficult here. Simply 1 2 line you will have to write. So let's see here. Denaturation of alcohol. Guys, keep this one in this one here, not necessary in which manner I have written, but I have written here so that if you make a notes of that and you could revise, because this question frequently asked and it's a very easy question. So let's see here. That was about the commercially important alcohols. Better you will get maximum benefit once or twice you will study this point. So maybe you will get some extra point if you are, and particularly if you are preparing for NEET examination. Okay, for the IIT main examination, that is also important, but not so much as it is important for NEET students. Now let's see. Then after that was about the commercially important alcohol. Then after, let's see, that means alcohol chapter finished, only mechanism left, and there will be 2 mechanisms in case of alcohol and 1 mechanism in case of ether. Now let's see here about the ether form. So firstly, preparation. First one is here. One thing you have studied there, when alcohol will be treated with dilute H2SO4, then there was formation of alkene. But so at greater temperature, when temperature is high, then the alcohol will convert into alkene. I have already discussed about this reaction. But when temperature will be less, then the alcohol will convert into ether. So at less temperature, when the alcohol will be treated with dilute H2SO4, then at higher temperature, alcohol will convert into alkene, and at lower temperature, alcohol will convert into ether, and at higher temperature, the alcohol will convert into alkene. At lower temperature, the alcohol will convert into ether, and at higher temperature, the alcohol will convert into alkene. About that mechanism of the ether formation and mechanism of alkene formation, that you will have to study. So about that we will get in detail when I shall discuss about the mechanism of the formation of alkene, and in the same time I shall also discuss about the mechanism of ether formation from alcohol. So that is here. Now mechanism about that we will discuss later on. Then the next point is, next method of preparation is Williamson synthesis. Williamson synthesis, what happened, what's here in the Williamson synthesis? The haloalkane will be reacted with sodium alkoxide. Haloalkane will reacted with sodium alkoxide. So halogen will combine with this sodium, form NaX. So valency of this oxygen atom become destabilized, and that of the carbon atom of alkyl group, that will also get destabilized. So this alkyl group will combine to this oxygen, and there will be formation of ether, and here sodium halide. Okay, and AX. Like as for example, suppose there is a compound here that will be reacted with sodium ethoxide, suppose. So what will happen? This sodium will combine with this chlorine, form NaCl. So the valency of this oxygen become destabilized and that of this carbon atom also destabilized. So this oxygen will bond to this carbon. So compound become its IUPAC name. Here this oxygen is separating this two alkyl group. So this one is a smaller length. Here no functional group anywhere other than apart from the ether. There is no functional group. In that case, you will have to consider about the length of the carbon chain only. Keep in the mind, when we will have to write the IUPAC name of ether, then if there be no any functional group in the compound, then we will have to consider about the length of the carbon chain. If there will be a functional group, then we will consider later on. So here in this compound there is no functional group apart from ether. That's why we will consider the length of the carbon chain. For the smaller length carbon chain, we will write the word oxy. So it's ethyl, so we will tell ethoxy. And for lengthier alkyl group, we will write only alkane. So its IUPAC name will be ethoxypropane. Okay, so that was about Williamson synthesis. One important point here which frequently asked in the examination, that is here this compound here. In this compound, when you will have to prepare the ether, in which one side there will be primary alkyl group and in the other side there will be tertiary alkyl group, then you will take the halide of primary alkyl group or of the tertiary alkyl group about that. That point is very important. That's frequently asked in the examination. As for example, when you have to prepare this is the ether in which there is tertiary alkyl group in one side and the primary alkyl group in the second side, like this ether. Here in this ether there is tertiary alkyl group in one side and the primary alkyl group in one side. So what happened here? So how to prepare? So you will take haloalkane of primary alkyl group and the sodium salt of sodium alkoxide of tertiary alkyl group. So when we will have to prepare the ether in which there will be primary alkyl group in one side and the tertiary alkyl group to the other side of oxygen, then we will have to take primary haloalkane and the sodium salt of tertiary alkyl group. So what happened here? So reaction, okay, that's in that manner. Here reaction will take place. That sodium will combine with this bromine, form NaBr, and this methyl group will bond to this oxygen. So in this manner the reaction will take place. When you will take tertiary haloalkane, if you will not take, what happened here? Tertiary haloalkane when you will take, then there will be cleavage of this bond, carbon halogen bond cleavage will be. If there is Br, so you may also take Br. So what happened? Very easily this bond will dissociate. Very easily the bond between carbon and halogen will dissociate because tertiary carbocation is stable. So what happened here? Here carbocation will form and this carbocation stabilize by attracting the electron of CH bond, like this compound here. Suppose this carbon here positive charge, here is this one, This one here, this carbocation I have written in expanded form. So this shared pair of electron will come here for double bond formation, and it will release as H plus ion. This hydrogen will release from there, and this shared pair of electron will come here for double bond formation. So product will be so alkene formation. Either this hydrogen will come or this hydrogen or this hydrogen. There is total 9 hydrogen attached here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So probability of release of H plus ion and the formation of double bond between carbon-carbon will be very high. So H plus will release from there and there will be alkene formation. So when you will take the tertiary haloalkane, then there will be formation of alkene instead of ether. Yes, ether will form, then that will be in very small quantity. So when you have to prepare the ether in which there will be tertiary alkyl group in one side and the primary alkyl group to the other side, then you will have to take a haloalkane of primary alkyl group and sodium salt of, that means sodium salt of tertiary alkoxide instead of tertiary haloalkane and sodium salt of primary alkoxide, because the tertiary haloalkane will dissociate to form alkene. So during that course there will be formation of alkene as a major product. So that's why when we will have to prepare the ether in which there will be tertiary alkyl group in one side and the primary alkyl group in the other side, then we will have to take sodium salt of primary alkoxide, then we will have to take sodium salt of tertiary alkoxide and the primary haloalkane. Okay, that is here. Now let's see this question. Watch out this question. I have already discussed right now. Then after, let's see here. When you will have to prepare during the Williamson synthesis. This one is, this reactions is Williamson synthesis. What is Williamson synthesis? The haloalkane will be reacted with sodium alkoxide. Then the reaction will be called Williamson synthesis. When sodium alkoxide will be treated with haloalkane and there will be formation of ether, that reaction will be called Williamson synthesis. Now another one. Firstly, we have discussed here earlier, before these reactions, we have discussed that when we will have to prepare the ether in which there will be tertiary alkyl group in one side and the primary alkyl group to the other side, then we will have to take sodium salt of tertiary alkoxide and primary haloalkane. In the same way, when we will have to form the ether, when we will have to prepare the ether in which there will be benzene in one side, when we will have to prepare the ether in which there will be benzene in one side and the alkyl group to the other side, what to do then? That means this type of ether when we will have to prepare. So if you will take haloalkane, if you will take halobenzene or aryl halide, then there will be partial double bond characteristic between the carbon of benzene and the halogen. When you will take alkyl benzene or aryl halide, then there is partial double bond characteristic between the carbon and the halogen, and therefore their bond dissociation enthalpy will be more. When their bond dissociation enthalpy will be more, so it will be very difficult to cleave the carbon halogen bond. So during that course, you will have to take sodium salt of sodium salt of benzene, that is sodium phenoxide and haloalkane. So here sodium will combine with this chlorine, form NaCl, and there will be formation of this ether. This ether. Okay, so that is here. When we will have to prepare the ether in which there will be alkyl group in one side and the benzene in other side, then we will have to take sodium phenoxide and haloalkane, because when we will take haloarine, then there will be great requirement of greater energy to dissociate the carbon halogen bond, because there is partial double bond characteristic between carbon and halogen in case of haloarine. Okay, you may write that off. This question already we have discussed here. This one very easily you could do. Now physical properties, you are already aware about the physical properties here, but ether are miscible in water. Miscible in water means very small amount of ether could dissolve in water, because ether here already shown here, there will be hydrogen bonding between the water molecule and the ether, because here oxygen is here, so there is a lone pair phaeton, and in water the hydrogen of water molecule that will be electrostatically bonded to this oxygen. So that's why ether is slightly miscible in water. Miscible in water. Okay, and if the length of the carbon chain will increase, that will become immiscible. For the higher ether having higher molecular weight, that will be immiscible in water, but the ether having the less molecular weight, that will be miscible in water. Now let's see here. Then after that was about the physical properties. Then after is chemical properties. So in ether there will be chemical properties. One will be due to the cleavage of carbon oxygen bond. One reaction will be that type. And one will be electrophilic substitution reaction. So in the ether, electrophilic substitution reaction that will take place in that ether in which there is benzene at one side. At least one benzene there must be bonded to the oxygen. In that case, there will be electrophilic substitution reaction. So there is two types of reaction, chemical reactions you will have to study in case of ether. One is the reactions which takes place due to the cleavage of carbon oxygen bond, and the other reaction in which there will be benzene at one side to the oxygen, and that reaction in that molecule, the reaction will take place by electrophilic substitution. So let's see here. Firstly, let's discuss firstly about the reactions due to cleavage of carbon oxygen bond. Let's see here. Very simple here. Reactions is very simple. Like hydrogen will go to this oxygen. So, and bond will break from here. There will be formation of haloalkane and alcohol. Same here. And when you react alcohol with haloalkane, then also there will be formation of ether. But that reaction will be very slow. So before reacting the alcohol directly with haloalkane, you react the alcohol with sodium or NaOH, so that reaction will become fast. Now here alcohol that react with HX, same reactions there is. Now watch out this reaction. In this reaction there is partial double bond characteristic between the carbon and oxygen. So here the bond dissociation enthalpy will be more. Bond dissociation enthalpy more here, and here bond dissociation enthalpy less. That means bond dissociation enthalpy less here. Here bond dissociation enthalpy is more. Here bond dissociation enthalpy will be less. So obviously bond will dissociate from here. Bond will dissociate from here. So hydrogen here bonded to this oxygen. So there will be formation of phenol, and then after here this alkyl carbocation will form. So with this alkyl carbocation, the halogen will bond, and there will be formation of haloalkane. Okay, same this reaction. This one, reactivity of HI, the order of reactivity in the whole of the organic chemistry, the order of reactivity of HX will be HI maximum, then after HBr, and then after HCl, and that will be valid for whole of the organic chemistry wherever you will study. Why? Because here in HI the bond dissociation enthalpy will be least, and in HCl the bond dissociation enthalpy will be highest. So here HI will cleave very easily into hydrogen and iodine compared to that of HBr or the HCl. So that's why everywhere the order of reactivity of HI will be maximum, and HCl here in this one, among these three, HCl will be least. Now watch out this reaction here. This one here, just as in the mechanism that will get repeated. So we will discuss in that case. Let's see here. This is the ether in which there is tertiary alkyl group in one side and primary alkyl group is second side. So when HI react here, I am writing here in detail. In the previous reactions also I have not told you in detail. So here you watch out. This one will react with HI. Then obviously there is hydrogen that will bond to this oxygen. So hydrogen will get bonded. So compound become and here will be a positive charge to this oxygen, because what happens when hydrogen H plus will go there, then the oxygen will give one electron to this H plus ion, and through other electron it will do bond formation. So obviously for this oxygen there will be loss of one electron. So that's why one positive charge will appear on this oxygen. Then after what happen, challenge is here, bond will dissociate from here or from here. From where the bond will dissociate? So watch out here, if bond will dissociate from here, there will be formation of tertiary carbocation, which will be stable. So that's why bond will dissociate here. But if a bond will dissociate from here, then there will be formation of primary carbocation. And among the tertiary carbocation and primary carbocation, the tertiary carbocation is more stable. So that's why bond will dissociate from here. So product will be here CH3 oxygen here, because bond has been dissociated between this carbon and this oxygen, and with this one, with this tertiary carbocation. So obviously this tertiary carbocation here the halogen will get bonded, and that will form haloalkane. So when there will be ether in which, if the ether in which there is tertiary alkyl group in one side and the primary alkyl group to the other side, when that ether will be treated with hydrohalic acid or hydrogen halide, then the cleavage will take place. Then the cleavage will take place between the oxygen and the carbon of tertiary alkyl group. As a result, there will be formation of tertiary haloalkane and the alcohol of primary alkyl group. Okay, that is. Watch out these reactions here. What is that? In this compound here, when in the ether in which there will be alkyl group of different length, ether in which there will be alkyl of different length, then alcohol will form of longer carbon chain and the haloalkane will form of the smaller carbon chain. So here in this ether, This oxygen is separating this alkyl group, and this alkyl group, this ether, this oxygen is separating this alkyl group here another, and this alkyl group here. So this chain is of 4 carbon, and this chain this chain is of 2 carbon, and this chain is of 4 carbon. So what happened? So bond will dissociate from here. So alcohol will form of this carbon and alkyl of this one. Watch out here. This one is tertiary carbocation and this is primary carbocation. So bond will dissociate. This is tertiary carbocation and there is primary carbocation. So bond will dissociate from here because tertiary carbocation is stable. So to this carbon, hydrogen will bond to this one, and to this carbon, the HI reacting. Yes, so iodine will combine to this carbon. So there will be formation of propanol, and its name will be 1-iodo-2,2-dimethyl propane. Okay, that is now in this compound. Watch out here. Oxygen is bonded to this benzene here. Oxygen is bonded to this benzene. So here will be partial double bond characteristic. So here bond dissociation enthalpy will be high. Bond dissociation enthalpy. Enthalpy means you just consider right now as energy only. So bond dissociation enthalpy will be high, and here bond dissociation enthalpy will be less. So that's why bond will not dissociate from here. Bond will dissociate from here. So that's why in this case, because the bond dissociation enthalpy between this carbon and this oxygen is high, and between this one is less compared to this bond. So that's why between these two, the cleavage will not take place. Let's see here just. Between these two, there will be partial double bond characteristic. That's why there will be bond will not dissociate from here. So bond will dissociate from here. So hydrogen will be bonded to this one. So there will be formation of phenol, and iodine will bond to this carbon. So there will be formation of 1-chloro-1-phenyl methane. Okay, what's the IPAC name of this compound? Because this carbon is containing functional group, so that's why 1-iodo-1-phenyl methane that will form. After that, let's see electrophilic substitution reaction. Electrophile, what is that? Electron loving or electron seeking. That is electrophile. So what happened? Ether, as in case of phenol, the electron go inside the benzene. So like that of OH, the alkoxy group will be also an activating group, and that will increase the electron cloud density at ortho position or at para position. How's when you will draw the structure, resonating structure. Once again, I am drawing the resonating structure of ether, but I have taught you a number of times, so that should be in your mind, and better you go through that videos also. But even though I am here drawing the resonating structure of this compound, okay, that will take some extra time, but okay. Let's see here how's that. This lone pair of electron will come here for double bond formation. So valency of this carbon atom become destabilized. So this pi electron will come to this carbon. So resonating structure will be, there will be double bond between carbon and carbon of benzene and that of the oxygen here. Here 2 electron has been involved in the bond formation. What this oxygen did? It has donated 1 electron to this carbon, and through other electron it has done bond formation. So that's why 1 unit positive charge will appear on this oxygen. Electron, this pi electron has came to this carbon. So here this electron, so there will be negative charge here, because this carbon atom to this at this carbon atom 1 electron of its own and 1 electron of this carbon has came. So this carbon got 1 extra electron. So that's why 1 unit negative charge will appear here. After that, between these two carbon, this lone pair of electron here come for the double bond formation. So this carbon leave this pi electron, and both the electron will come to their adjacent carbon atom, that means this carbon. So next resonating structure will be This will be the resonating structure. Then after this pi electron will come here between this carbon and this carbon. This lone pair of electron will come for the double bond formation. So this carbon will leave this pi electron and both the electron will come to this carbon. After that, this lone pair of electron come here for the double bond formation and this oxygen will take the electron. So next resonating structure will be again there will be two lone pair of electron and here. So this structure, this resonating structure and this first resonating structure is same. So that's why no need to draw this resonating structure. So actually there will be only 4 resonating structures. They are shown 5, but actually there is, in the real sense, there will be 4 resonating structures. Okay, so that is here. So watch out here. Electron has came at ortho position, here para position, and here also ortho position. So there is electron cloud density maximum at ortho position and at para position. So when any electrophile will approach towards the ether in which there is one side benzene, then the electrophile will bond either to the ortho position or at para position. Let's see the example. First example is halogenation. So here let's see halogenation here. So when bromine you are reacting with in presence ethanoic acid. Ethanoic acid here is the solvent. So one bromine here, one bromine will bond to the carbon of ortho or para, whatever be that. From there, the hydrogen will release and that hydrogen will bond to this bromine. So there will be formation of here bromine substituted here and HBr. In other compound, HBr has been not shown. Here HBr formed, but that is the byproduct. That's why it has not written. And in the same way, the bromine will bond to the carbon of the ortho position, and so there will be formation of here this one one bromo one methoxide, one bromo 2 methoxide benzene. Either that will be the name or that is also called 1 2 here. So 2 bromo anisole. Yeah, anisole, particularly when methyl will be bonded to the oxygen. This compound is called anisole. Anisole is when that will be called anisole when the methoxy group will be bonded to the benzene. Then that compound is called anisole. So of this anisole, bromine has been bonded to the ortho position. So common name will be ortho bromo anisole, or IPAC name will be this one. That is here one electrophilic substitution reaction. Next one, Friedel-Crafts reactions. So Friedel-Crafts reactions, that is two types: Friedel-Crafts alkylation and the Friedel-Crafts acylation. Friedel-Crafts alkylation and Friedel-Crafts acylation. In both the cases, in Friedel-Crafts alkylation as well as in Friedel-Crafts acylation, catalyst taken will be anhydrous AlCl3. This is what's the name. The name of the catalyst is very important for your CUT examination and for the NEET examination, because question directly asks which catalyst taken during the Friedel-Crafts reactions. So catalyst will be anhydrous AlCl3. So what is here? In presence of anhydrous AlCl3, you know that is here this alkyl part will bond to the carbon of ortho or para. From hydrogen release, that will combine with chlorine, form HCl. So that is here. That's why ortho and para substituted product will form. Same here, acyl halide here taken. So same, chlorine will bond to the hydrogen of ortho position or of para position, ortho position or of this para position. So form HCl and C double bond O, that will get bonded to this side. Listen how to write the IPAC name of this compound. This one. It is ketone. It is ketone. So actually this one oxygen is doubly bonded here and this carbon is bonded here to this methyl. Actually that is the structure. Might be you know, very easy. So 1, 2, that is main chain, because open chain is containing the functional group. That's why open chain is containing functional group. That's why the name of the compound will be based on open chain. I am telling you about the IPAC name. This one is here, this one is common. This one is common name. IPAC name I am telling you. So now here it is bonded at the first position. There is benzene. So carbon atom which is bond of benzene, which is bonded to the open chain, that will get one position, and it will be second position. So at first position there is 2-methoxy phenyl, 2-methoxyphenyl, and this is ethanol. So ethanol. So IPAC name of this compound will be 2-methoxyphenyl ethanol, and common name will be 2-methoxyacetophenol. Okay. Same nitration here, that is only left here the formalities, not here, because already you are aware about these reactions. So only formalities left here, which I am doing here. So nitration, so NO2 group will attach at ortho position or at para position. Same that is here. That's completed. These questions you do by yourself. Okay guys, these questions I am doing. Here, this length oxygen here, this is longer carbon chain. So that's why alcohol will be of longer carbon chain. And bromine will combine to the smaller length carbon chain. This reaction also you could do that. Bond will not dissociate from here, bond will dissociate from here. So that's why there will be formation of phenol and C2H5Br. You do here will be H2SO4 and HNO3. So there will be electrophilic substitution reaction. NO2 will bond to the ortho position as well as at para position. So a compound will be here. To the ortho position, attach the NO2, and that will be minor product, and major product will be when NO2 will be bonded to the para position. Okay, this question you do by yourself. Tertiary carbocation here will be more stable, so iodine will bond to this tertiary carbocation and hydrogen to this one. So ethanol and alkyl group of tertiary carbocation will form. These reactions you do by yourself. Very easy it is. Okay, very easy it is. So you do that. Okay, it's all for this ether preparation. Now we will discuss about the mechanism of reactions in the next class. It's all for this class. In the next class we will discuss about the mechanism of the reactions. That is, there will be 3 mechanisms. About that we will discuss in the next class. Thank you, Team Educate.